There's four variables that are important when discussing the behavior of gases. We have pressure represented by a P, volume represented by a V, temperature, which remember has to be in Kelvin, represented by a T, and the amount in moles. The relationship of these variables can be described in the following gas laws. And these gas laws help us predict the behavior of gases when the conditions change. So you'll notice in all of these gas laws, on one side they have the numbers 1, which would be initial conditions, and then the second side has the numbers 2, which would be the final conditions. You can tell which laws which variables the laws represent by the letters. So Boyle's talks about the relationship between pressure and volume. Charles between volume and temperature. Gay-Lussac's between pressure and temperature. The combined gas law really does have the combination of the three gas laws above it. And then Avogadros Law, which discusses the relationship between the volume and the amount. Now, because there's four variables that are used to describe a gas, notice that when the variable is not used in the law, it has to be held constant. So, for example, Boyle's law uses pressure and volume, and so then the things that are held constant are the remaining two, temperature and amount. Or we can look at Charles' law, which uses volume and temperature, and so the things that are held constant are pressure and the amount. So if the variable is not in the gas law, it means that that variable is held constant. Another important thing that the gas laws help us do is predict qualitatively, not using numbers, how the conditions change. Boyle's law, you see over here, is something that is inversely proportional. When something is inversely proportional, it means that they change in the opposite directions. So, for example, I'm just going to write here opposite. So it's an opposite change. So, for example, back here at Boyle's law, if I increase the pressure, then at a constant temperature and amount, that would cause a decrease in volume. You see, the opposite is an increase causes a decrease. Or, for example, if I increase the volume, then the opposite would happen, the pressure would decrease. So Boyle's law has an inverse relationship between the conditions. They move in the opposite direction, inversely. Now, mathematically, you can notice the difference. Boyle's law is the only one where the two variables are multiplied. Charles' law, Gay-Lussac's, and Avogadros' law all have them divided. These type of relationships are what we call directly proportional. So when these two conditions are directly proportional, it means that they change in the same direction. So, for example, if I'm looking at Gay-Lussac's law, if an increase in the pressure also results in an increase in temperature, they do the same thing. Or if I decrease the temperature, that would result in a decrease in pressure. So they change in the same direction. And that's what it means to be directly proportional. So knowing if something's directly or inversely proportional allows us to predict what would happen before we even do the calculation. So the other thing we do with the gas laws is calculations, where we're given information and we plug it in. So in this video, I've taken each of the gas laws and have a problem here where we can see how that works. So the first one is Boyle's Law. And Boyle's Law is P1 times V1 equals P2 times V2. We would know that temperature and the amount are held constant, but in these problems, if that's not mentioned, you can assume that those two are held constant in how the book and things are written. So Boyle's Law, just to mention, Boyle's Law describes and helps us understand respiration. So before we go too much further, let's talk just a little bit about Boyle's Law. So it has an inverse relationship, which means pressure and volume change opposite of one another. When you breathe and you breathe in, what happens is your lungs expand, so volume goes up. As the volume of your lungs expand, that causes the pressure to go down. This allows inhalation because the pressure on the outside is greater and the air is drawn into those lungs. When you exhale, the opposite happens. Your lungs get smaller, so the volume goes down. What that causes is the pressure to go up. So now the pressure in your lungs is higher, which causes the air to be expelled, or you exhale. So it's kind of fun to think about Boyle's Law, just qualitatively describing how air is able to come in and air goes out of our lungs. Now this problem doesn't have an example with lungs, but it is a problem with Boyle's Law. It says a sample of helium gas. Now most of the time the gas or mixture of gases that are involved are irrelevant because these gas laws work with any gas or mixture of gases. But it tells us in this problem we have helium gas and it has a volume of 2 liters. And it tells me that the pressure at that volume is 4 atmospheres. The question then is, what is the volume of gas? So they're asking me to find a new volume if I change the pressure to 6.7 atmospheres. So let's first think about what we think if the pressure will go up the volume will go up or down. So comparing our pressures, what we notice is we have an increase in our pressure. Boyle's Law is inversely proportional, which means then my volume must decrease. So I'm going to expect to have a volume that is less than 2 liters. As far as the units go, you can use milliliters or liters for the volume, and any of the units for pressure to solve these problems, as long as the units are the same on both sides of the equation. So we're good. So pressure 1 times volume 1 equals pressure 2 times volume 2. Plugging in the numbers, I get 4.0 atmospheres times times 2 liters equals 6.7 atmospheres times volume 2. You can kind of think of that. If the units are confusing to you, sometimes people take off the units to complete the math. Now I'm solving for volume 2, so I would divide this side by 6.7 atmospheres to have it cancel. Then I would also divide this side by 6.7 atmospheres. The atmosphere units cancel, leaving me with units of liters, which makes sense because I'm trying to calculate a volume. So I would take on the numerator 4 times 2 and divide that by 6.7. And my new volume, when I calculate it, volume equals 1.194 liters. Looking back at what I was given, 2 significant figures seems appropriate, and I get 1.2 2 liters. I feel good about this answer because I know the volume should have decreased, which it did. It was less than 2 liters. So this is how you solve for using Boyle's law. Now moving on to Charles' law. So Charles' law helps us understand the relationship between volume and temperature. This type of relationship is a direct relationship. Which means if volume increases, the temperature will do the same and increase. Charles' law helps us understand hot air balloons. If you've ever been around a hot air balloon, they have a heater, and that heater, as you would imagine, increases the temperature of the air that's around it. Well, Charles' law says if we increase temperature, the volume will also increase. So hot air will take up a larger volume, filling the hot air balloon. So let's see how Charles' law can be used in a calculation. So this says we have 25 liters of a gas. So we have a volume of 25 liters. They did not tell us what gas, but that's okay. We can still do the problem. They tell me I have a temperature of 35.7 degrees Celsius. Now remember that you must use Kelvin in order to solve these problems. So if you aren't given Kelvin, then you need to convert to Kelvin in order to finish the problem. I usually do this right away. And this tells me I have 25 liters of gas at 35.7. It's cooled to 20 degrees Celsius. What is the new volume? So they want me to calculate what the second volume would be if I change the temperature to 20.0 degrees Celsius. Now remember to convert it to Kelvin. Now before we get going, let's take a look and see if we can predict if the new volume would be larger or smaller. So looking at our temperatures, we see that I added incorrectly. You might have been yelling at me. It should be 293. Sorry. So my temperature decreased. They told me it cooled. And so Charles' law is directly proportional. So if the temperature decreases, the volume also will decrease. So I would expect my new volume to be less than 25 liters. Well, let's plug in and see. So I have volume 1 over volume 2, volume 1 over temperature 2 equals volume 2 over temperature 2. So let's plug in 25 liters divided by 308.7 Kelvin equals volume 2 divided by 293 Kelvin. Now I can cross multiply, and so I'm going to multiply both sides by 293 Kelvin. That causes that to cancel, and then I'll multiply this side by 293 Kelvin. My Kelvin units will cancel. So my new volume is going to equal, I'm looking now at this side of the equation to figure out what I'm going to plug in. So I have 293 times 25, that's in my numerator, and then I'm going to divide that by 308.7. And I get 23.7285. This would be in liters because my Kelvin canceled. Looking back at what I was given, 3 significant figures seems appropriate. So I'd have 23.7 liters. I had predicted earlier that the volume would decrease as I cooled it, and it did decrease from 25 liters. So that makes me feel good about my calculation. So let's take a look at Gay-Lussac's law. You might notice a theme in these. They're all very similar. We're given 3 of the 4 variables and asked to solve for it. Gay-Lussac's law demonstrates the relationship between pressure and temperature, with volume and the amount held constant. Again, just like Charles' law, when you have these type of ratios or fractions, mathematically these are directly proportional. Which means as pressure, whatever pressure does increase, then temperature will do the same, increase. Or if it decreases, then both of them would decrease. Gay-Lussac's law, I think a lot of times about my dad with Gay-Lussac's law, because I think about the air pressure in my car tires. So my dad always wanted me to know how to fill my car tires, and he told me that when you look in the door of your car, you see the optimal air pressure for your tires, and it usually says cold or cool. And so this Gay-Lussac's law helps me understand. So when you drive your car on the freeway or the road, the friction of the tires on the road causes an increase in temperature. Well, Gay-Lussac's law says if you increase the temperature, that will also cause an increase in pressure. So if you've been driving long distances and then you measure your car tire, it would actually have a higher pressure than you might expect. It would be appropriate, and your car tires can handle that pressure, but you wouldn't want to fill your tires based on that pressure because an increase in the temperature has caused it to be higher. It's also the same reason if you live in a climate that gets cold weather, that if your tire pressure is near the borderline of its optimum pressure and you have a car that indicates when you have low tire pressure, that in cold mornings your car may tell you that your tire pressure is low, but once you drive around a little bit, that light goes off. Again, it's Gay-Lussac's law that helps us understand. As the temperature goes down, the pressure goes down. And again, as you drive around on the road, the temperature increases, building the pressure back up. Gay-Lussac's also helps us understand things like a pressure cooker. In pressure cookers, you let the pressure inside build up. So as pressure goes up, the temperature goes up. That hotter temperature allows our food to cook faster. So that's kind of qualitatively what Gay-Lussac's law helps us understand. But then a lot of times they want us to do problems with it. So let's take a look at this one. It says the temperature of a gas sample at 25 degrees and 1 atmosphere. So they tell me the temperature is 25 degrees Celsius. And I want to be sure to add 273 to that. So I get it's 298 Kelvin. Because remember, for all the gas laws, you must be using a temperature unit of Kelvin. Tells me that my pressure is 1 atmosphere. 1 atmosphere is standard pressure at sea level. Then it says I changed the pressure, the temperature to 200 degrees Celsius. That's a big change. Let's see what happens to the pressure. So I'm going to add 273 to that. So that's 473 Kelvin. They want to know the new pressure in atmospheres. Now thinking again qualitatively on this one, if I increase the temperature, so temperature has increased, we know that Gay-Lussac's is directly proportional, so if the temperature increases, the pressure should also increase. So I expect the pressure to be greater than 1 atmosphere when I calculate it. So let's plug in. The initial pressure is 1 atmosphere, and remember, you can use any unit for pressure. The temperature is 298 Kelvin to start with. I'm trying to find the new pressure, and my new temperature was 473 Kelvin. So I'm going to cross multiply, so 473 Kelvin, that cancels on this side, and then 473 Kelvin. So I'm going to multiply, the kelvins cancel. So my pressure now is by itself. And I will multiply 473 times 1. And then divide that by 298. Oh, sorry, I cleared it. 473 divided by 298. And I get 1.587. That would be liters. Oh no, atmosphere, sorry. I was not paying attention closely enough. And to 2 significant figures, it would be 1.6 atmospheres. Honestly, to tell you the truth, I feel like I was expecting a greater pressure change. The pressure did go up, so that is true, but I was expecting a greater pressure change from such a big temperature change, because we went from 25 degrees to 200 degrees. But mathematically, it just comes out to 1.6 atmospheres. So the combined gas law is really just what it says, the combination of all the gas laws. So we have, in this case, you'll notice the only thing that's held constant is the amount. And I'm going to write it down here. So we're going to have more pieces of information and more data to plug in. So it says the pressure inside a 1 liter. So that's my volume. I can tell by liters. Is at 25 degrees. So that's my temperature. I'm adding 273 to that. So that's the 298 again. And then the pressure is 750 millimeters of mercury. What is the pressure? So pressure 2 is what we don't know. When it's heated to 30 degrees, so my second temperature is 30 degrees Celsius. So that is a plus 273. So that's 203 Kelvin. And then placed in 7.5 liters. And they want to know, I'll erase that. They want to know P2. I'll erase it from here. Okay, so before we plug this problem in to solve it, what I would like to do is show you how we still can use the indirectly and directly proportional to figure this out, if it's going to increase or decrease. So we're trying to find a new pressure. So first of all, we look at our volume. And so volume decreases. Now, if we think about pressure and volume, that's Boyle's law. So usually a decrease in volume would cause an increase in the pressure. And then we look at our temperature, and we see that the temperature is increasing. Now, volume, pressure and temperature is governed by Gay-Lussac's law, and that's directly proportional. So if temperature increases, I would expect pressure also to increase. So while it's a little bit harder to decide what's what when you have the combined gas law, both of the changes that are made to the system would indicate that my pressure should increase. So I'm going to expect the pressure to be greater than 750 milliliters. So plugging in, let's plug in here. I have 750 millimeters of mercury, and you can use any units of pressure, times 1 liter. On the top, I'm dividing that all by a temperature of 298 Kelvin. And this whole side right now, those are all numbers. We know everything on that side. I'm looking for the pressure of 2, and the volume is 0.75 liters, and the temperature is 203 Kelvin. So if you don't mind, I'm going to erase this part right here since I've already used it so I can complete the work there. All right, so first I'm going to multiply 203 to the other side. So I'd have 203, and you can practice your algebra. You don't have to do it just the way I'm doing it. Times 1 liter, that's on the top. And then if I stop there, there's 298 Kelvin. That would equal P2 times 0.75 liters. Now I would divide both sides by the 0.75 liters to get P2 by itself. So I have the top is going to stay the same. Divided by, I still have 298 Kelvin, but I'm also going to bring over the 0.75 liters. Liters cancel, Kelvins cancel, and I have only millimeters of mercury left. So it's 203 times 750 times 1. And I'm going to divide that by, and I'm putting it in parentheses. So on my calculator, I'm putting it like this. 298 times 0.75. And I get 681, and I don't have, it's 681.2. I don't have very much room, so I'm not going to write the whole thing. And it would be millimeters of mercury. So my pressure 2 would be 681, which is an increase from 750, which makes me see I did predict an increase. So in the combined gas law, you see that you actually have 5 things that you're given, and you'll solve for the 6th one. Again, if you got to the point where you could see where it was plugged in, but you didn't like how I rearranged it, you practice your algebra by yourself and see if you can recall how you did it, or come talk to me and I'll look at and help you get going. We have one more gas law that uses the similar ideas, Avogadros Law. And Avogadros Law is the relationship between volume and the amount of gas. And the amount of gas is going to be in moles. So this says a sample of nitrogen gas. Again, the beauty of these gas laws is they can be used for any pure gas as well as combinations of gases. Gases are have so much space and are so far apart that they mix uniformly when they're in a container. So the nitrogen gas has 5 moles, so N1 equals 5 moles in a volume of 3.5 liters. Calculate the new volume, so that's what we don't know, if the moles are increased to 10 moles. Now, Avogadros Law, how it's set up is mathematically, this is directly proportional, which means that volume and the number of moles will change in the same direction. So here, the number of moles is increased from 5 to 10. So I expect the volume to also increase because they are going to move in the same direction. So plugging in, here's where we start. And then the volume is 3.5 liters over 5 moles. This is going to equal 10 moles on the bottom and V2. So to solve for V2, I'm going to move the 10, cross multiply it over, so 10 cancels here, and then we have to put it over here. So I have 10 moles times the 3.5 liters, 10 times 3.5, divided by the 5 moles. So the moles cancel. And our new volume equals, I just get 7, but I know I have to have 2 significant figures. My calculator never gives me the 0. So it's 7.0 liters is the new volume when you change that. Now look at this. You doubled the number of moles, and look what happened to the volume. 3.5 times 2, you doubled the volume. So you could have even looked at that and said, well, I know since you doubled the moles, I'm going to double the volume, and just said 3.5 times 2 and gotten the answer. So that's kind of a shortcut. Now there's one more idea, and we can use this as well to do calculations. And this is something that's called STP. STP stands for Standard Temperature and Pressure. So these are defined values, and if you see a problem that says the condition is at STP, like that, what it's telling you is the pressure is 1 atmosphere, or anything that's equal to it, and the temperature is 273 Kelvin. At STP, there's a relationship that often helps us solve problems, and that is that 1 mole of any gas or mixture of gases has a volume of 22.4 liters. And that will be true for any gas at STP. So when I see this at STP in a problem, I always like to think about this relationship right here and see if I can use it in an equation to solve it. So I have 2 problems that I could use it, and I wanted to give you an example. So it says, how many liters does 2.8 moles, so I know 2.8 moles of nitrogen gas, and remember the standard conditions are true for any gas or mixture of gases. It says, how many liters does it occupy at STP? So in my mind, when I see at STP, I know that 1 mole of any gas or mixture of gases is 22.4 liters. Remember, anytime we have an equality, we can use it to make a conversion from one unit to another. So I'm going to use this. I will put the 1 mole on the bottom so it cancels, and the 22.4 liters on the top. So if I have 2.8 moles of any gas at STP, I can determine I get 62.72 liters, so that would be 63 liters of gas. And this says nitrogen, but this is true for any gas. Now let's try another one. It says how many moles does 25 liters, so of O2 contain, and there's that magic at STP. So when I see at STP, I remember this relationship because it's very helpful. 1 mole of any gas or mixture of gases is 22.4 liters. So I write down what I'm given, And if I put the 22.4 liters on the bottom, so the liters will cancel, and the 1 mole on the top, I can determine that 25 liters of oxygen would have 25 divided by 22.4, 1.116 moles of oxygen, to 3 significant figures, 1.12 moles of oxygen. Now, if they asked me to find grams, I could do that using the molar mass if I had to, and then I would have to know it was oxygen. But in this problem, I've solved it because all they wanted to know was how many moles.